Hello, stats class. Here is lesson 7.2b, which is continuing the idea of sample proportions, but now we're going to switch to doing probabilities for those sample proportions. So let's talk about how to calculate a probability for a particular p-hat or a particular sample proportion. And what's interesting about that is we've already learned how to do it in chapter 6. We're going to change approaches a little bit in chapter 7, and I'm going to show you both methods. In fact, I guess I'm going to show you 4 methods now that I think about it, but that's okay. Small samples first. Let's start with small samples, which means that I'm going to talk about situations where the normal condition is not met. And that would mean that NP or NQ are less than or equal or less than 10, because greater than or equal to 10 is what would cause us to use the normal approximation. So let's first talk about what if you can't use the normal approximation. And that means we're basically dealing with a binomial probability. Like in chapter 6. So I'm going to do an example, and I'm going to do 2 methods on this, the chapter 6 method and then shifting into what we're doing in chapter 7 so that you can see them side by side. Let's just write down what the example is. Let's say we have 80% of all middle school students plan to go to college. Now let's say that's the population value. So this is P without the hat because it's the population value, it's the parameter. And I take a random sample of 10 students. From this population, and I ask them, do you plan to go to college? And I find a p-hat value. P-hat, remember, is the proportion of the sample, the proportion of those 10 students who are planning to go to college, and it might not be the same as 80%. So this might be higher or lower than 80%, and I'm okay with that. And specifically, I want to know the probability that that small sample has more than 90%, 90% or more. So I want to know the probability that my p-hat that I calculate from my sample is greater than or equal to 90% or 0.9. So that means probability of 9 or 10 of these students saying, yes, I plan to go to college. There are 2 ways to do this. One way is to think about the total. So the chapter 6 method is looking at the number of successes. Chapter 7 method is looking at the proportion of successes. And I'm going to do both because I want you to see that they come out the same. Proportion of successes. Actually, I take it back. I'm not going to show you 2 methods on this one. It's on the large samples that I'm going to show you 2 methods. So I'm going to say chapter 7, that's this. I'm not going to say this is a separate method. This is just, if you're thinking chapter 7, you're thinking proportion of successes is 0.9, probability that p-hat is greater than or equal to 0.9, given that p is 0.8. That's the chapter 7 thing. But we're going to use a chapter 6 method to do this because my normal condition is not met. So you don't have to write this part down, but that 10 students is a really small sample. And if I do n times p, which is 10 times 0.8, that's only 2 students. That's way less than the 10 that would make it big enough for the normal condition. So I can't use a normal curve. But what I can do is I can use what we learned in chapter 6. I can say this is the same as the probability of x being greater than or equal to 9. And remember, x is the number of successes. So I'm talking about out of those 10 students, the probability that 9 or 10 of them say yes. That's the same as the probability of x equals 9 plus the probability of x equals 10. And if the normal condition is not met, I said it wrong a minute ago. I said I was going to show you two methods, and it occurs to me there's no way to do this other than do it with the binomial formula. That's what we're going to do. So we would do the probability of 9 and the probability of 10 added together. Remember the binomial formula? I love the binomial formula. It's one of my favorites. It's this one. It has the probability of success, that's 0.8, to the number of successes, and the probability of failure to the number of failures, and then you have to do it again for the 10. Okay, that's fine. 0.8 to the 10th and 0.2 to the 0. You might notice that this 0.2 to the 0 is not important. It's 1. It goes away. It doesn't change the problem. C1010 is also 1, so you could just do 0.8 to the 10 because these two pieces are 1. Or you could just type this whole thing in your calculator, and that's fine. I'll type it just to prove that it works, but there's a faster way that I'll show you in a sec. So what I've got is 10 math probability C9 times 0.8 to the 9th times 0.2 to the 1. I don't have to type the 1, plus 0.8 to the 10th, which is the probability that all 10 of them say yes. And I got 0.3758. I'm going to put this in parentheses because we're thinking this, but we're actually doing a chapter 6 problem. All right, you could have done it that way. Or sometimes there's so many of these that you don't want to add them all up and it's a pain. So you use the CDF instead. And remember that that is always an option. Greater than or equal to is not what CDF does. It does less than or equal to. So I could do 1 minus the probability that x is less than or equal to. Don't say 9, because less than or equal to 9 is not the opposite of greater than or equal to 9. I have to leave off that 9. So if I'm thinking all the numbers from 1 to 10, right? If I'm greater than or equal to 9, that's the opposite of less than or equal to 8. I have to do less than or equal to 8. And that's a binom CDF, which we learned in chapter 6, and I hope you haven't forgotten it. Remember, we need n, p, and k in this spot. So n is 10 sample size, p is the 0.8, which is from the 80%, and k is the number I'm interested in, which is 8. So I could also type it that way. I should get the same exact answer, but let's just make sure. So second vars towards the bottom is binom CDF, and n and p and k. And don't forget you have to do 1 minus that, which is 0.3758. Isn't that comforting that it came out the same? So it's about a 38% chance. And that is also the probability of this. Probability of p hat, the sample proportion, being bigger than or equal to 90%, given that the population is 80%. And I can't use the normal approximation, or if I did, I would get a very different answer than this because this is such a small sample I mean, we could make a histogram out of it and it would be kind of jaggedy histogram. I'm not going to draw it perfectly. And it's not close enough to normal to use the normal curve. So we're just not going to do the normal approximation on that. Okay, so that's what you have to do for small samples. You have to think back to chapter 6. If you have large samples, let's do that next. If you have large samples and you're doing the same sort of problem, what that means is that the sampling distribution would be approximately normal. And remember that the way you check that, the normal condition, is if NP and NQ are both greater than or equal to 10. So I'm going to do a bigger sample this time and say, let's say we have a sample of 100 students. Same situation, 80% in the population. We do a random sample of 100 students. And so I can check to make sure that this is actually going to work. NP would be 100 times the 80%, which is 80 students. That's bigger than 10. NQ is 100 times Q is 0.2. So that's 20, and that's also bigger than 10. So this is okay to use the normal approximation. And I will say you could always just do this every single time. Since we have the CDF command on our calculators, it's not such a big deal to do that. We can talk about that if you want, but it's traditional and probably better just so that we are consistent. It's traditional to use the normal distribution whenever we can. So I'm going to show you again both ways of thinking about it, Chapter 6 and Chapter 7. You don't have to write down the Chapter 6 method if you don't want to. But Chapter 6, you would think to yourself, I'm trying to find the probability. Actually, let me do the Chapter 7 setup first. You're going to do the probability that x is greater than, not x, p hat. Yeah, that's the difference. So probability that p hat is greater than or equal to 0.9, given that p equals 0.8. Same exact question we asked before, except now we're going to do it with the normal approximation. And I will come back to this method in a minute. If you'd like to put your pencil down and just watch this piece for a minute, you can. It's the same as finding the probability that x is greater than or equal to whatever 90% of 100 is, which in this case is 90. So if I'm doing the binomial method, I would have to do probability of x equals 90 plus 91 plus 92 plus 93 plus 94 all the way up to 100. The reason they invented this normal approximation thing is people didn't want to do all that. But we could have done binom CDF and use, instead of 10 it would be 100, and instead of 8 it would be 89. You're welcome to try that if you want, but I'm not going to do it that way because the tradition, like I said, is to do the normal curve. So the normal curve means I need to find a z-score. Okay, so I'm going to take my 90 minus my mean. So I would be thinking to myself, what is the mean of x? What is the expected number of these 100 students that would say yes? If I have an 80%, then that expected number is 80. We actually already calculated it when we were doing this check of the condition. So that's 80, and I put that here. And then on the bottom, I need my standard deviation, which, as you might remember from Chapter 6, is the square root of NPQ, which is the square root of 100 times 0.8 times 0.2. And that comes out to, actually, it comes out really nice. Look at that. I'm going to type it just to be sure, but last year's notes, it came out really nice. So let's make sure I did it right. To 80 times 0.2, no, it's 100 times 0.8. That's where the 80 came from, times 0.2. That's 16. That's square root of 16, which is 4. Isn't that convenient? Came out really nice. So my z-score is 10 over 4, which is 2.5. And then I need to find the probability that z is greater than or equal to 2.5. And that would be normal CDF. I'm going to put a dot, 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 because we're going to do that same thing over here. And this is the part you really need. So I'm going to put a parenthesis this time around this part, because you don't have to do this if you understand this. You could do it either way. And part of my point here is that they're going to come out the same. But let's talk about this. If you're thinking Chapter 7, you're still going to find a z-score because we decided it's normal. So this time we're going to put our p hat here minus our, okay, what's the mean for p hats? The mean of all the p hats, remember? Mean of the p hats, we said was the same as the population parameter, which is p. That's 0.8. So that's cool. We didn't even have to calculate it. We just know that it has to be the same because p hat is naturally unbiased. So we're doing p for our mean. What's our standard deviation? Well, that was in lesson 7.2a notes. And we did a little bit of derivation. We took this formula and divided it by n and simplified it. And if you forgot what we did, it's PQ over n. So let's do that. PQ is 0.8 times 0.2, and then I'm dividing it by n, which is 100, and I'm square rooting it. Okay, so 0.8 times 0.2 is 0.16, and I'm dividing it by 100, so I get 0.0016. And then I square root that, square root that answer, and I get 0.04. Okay. So then I keep on simplifying. I got my mean and I got my standard deviation, and I simplify. This is 0.1 over 0.04, which is 2.5. Now, let's stop and think about that a minute. Is anybody surprised that it's 2.5? I think it's kind of fascinating that these are the same. And it's exciting that these are the same because it means that what we're learning right now is based on this. Basically, what we did is we took all three of these numbers and we divided them by 100 to get 0.9, 0.8, and 0.04. And when you divide all three parts of a fraction by 100, you get the same fraction you had before. You get an equivalent answer. So I still need to find the probability that z is less than or equal to 2.5. That's amazing. Or greater than, sorry, greater than or equal to 2.5. That's what I need to find. It doesn't matter whether you think of it as a total or think of it as a proportion, you get the same answer. That's my point. So let's do that. That would be a normal CDF, or it would be table A, and that would be fine also. I like normal CDF better. So this is kind of a sidetrack, so let's put a thing around that. 2.5 and 999, and plug it in the calculator. Say in bars, normal CDF, 2.5, 999, paste. And this time it's a really, really small probability. I got 0.0062, or less than 1% chance that this would happen with a sample of size 100. What does that mean? Let's talk about that just a little bit. So what we have is this normal curve with the mean at 0.9 and the standard deviation of 0.04, which means that this is 0.94. Oh wait, no, this is 0.8, sorry, and this is 0.84, and this is 0.88, and 0.89 is way over here. So 0.9 is way over here, and it's just this tiny piece is what we just found. That's a really unusual thing for a sample of size 100 to be this far off. 80% versus 90% is a big deal with a big sample, but with a small sample, it's not such a big deal. It's only 1% difference. So that's kind of evidence of what we've been talking about, that if you have bigger samples, you get closer to the true proportion, and it's more unusual to be far away from the true proportion. This graph that I didn't finish up here, if I had finished it, which I'm not going to because it's hard to get it accurate, but this one, because I'm just saying it's hard to get it accurate because it's not a normal curve, it's some other shape. But what I'm saying is that getting far away from, like maybe it'd be this area that looks like about 30%, right? And so the 0.8 is in the middle and the 0.9 cutoff is a lot less rare when we have a small sample. So small samples tend to have a bigger spread and you're more likely to get far away. Sorry, I don't think I explained that as well as I could have maybe, but I will try again a few more times in this chapter. So just to summarize, if you are trying to find a probability, the first thing to check is it a small sample or a large sample? You can do that by checking this NP and NQ thing. Are they both bigger than 10? If they are, you can use the normal approximation. If they're not, you have to use chapter 6 methods, which is the binomial distribution probabilities. So there you go. That is how to calculate probabilities for sample proportions, whether they're small or whether they're large. And you don't need to know this method so much because it's the same result as that method. If you're more comfortable with this, sure, do it. And on the project, I know in past years, some people have done this on the project instead of doing this, and that is fine. Either one of these is fine when you're doing your project. So I'm going to stop there, and we will go on the next video.